The PowerPoint is posted on Moodle too, and there is a narrated PowerPoint by Dr. Phil Vogel of our department. So just in case you want to review and see how he did his explanation, you can play it. But still, I'm recording this because I really need to explain it myself, just to make sure we are on the same page. So experiment 7 was supposed to be on heat and heat changes. So the instrument that's used is called a calorimeter. It's a calorimeter, a meter, calorimeter. So the process is called calorimetry. So under calorimetry, the scientific concept is thermodynamics. Thermo comes from the word heat. And of course, dynamics is the change of a system, how a system behaves. So it's heat changes, thermodynamics, the interaction of heat and matter, the study of the interaction of heat and matter. So there's going to be a system and surrounding when you study calorimetry. For our case today, the system will be either sodium hydroxide and HCl. Those are the guys taking part in the reaction, and sodium hydroxide and acetic acid. So these are the two systems. When I say system, I'll be referring to these two. One of these two, HCl and sodium hydroxide, acetic acid and sodium hydroxide. HCl is a strong acid, acetic acid is a weak acid. You learn that in general chemistry. So the formula for acetic acid, which is the active ingredient in vinegar, is HC2H3O2. That's acetic acid. The Lewis structure of acetic acid is this. This is the Lewis structure of acetic acid. So it's a carboxylic acid. It's an organic acid. It's a weak acid compared to HCl. But both of them do undergo neutralization. When acids react with bases, with hydroxides, you get a salt and you get H2O. Okay? Just swapping the first element. That's what you're doing. So sodium will swap the hydrogen. Here you get what we call sodium acetate. Okay, let me see. I think someone is chatting. Oh, okay, I need to admit someone logging in with a different email. Okay, so you get sodium ethanoate, sorry, and water. When acetic acid reacts with sodium hydroxide, you get sodium acetate or sodium ethanoate and water. But the other product that's not shown here in the balanced equation is heat. So you're going to get heat with these two reactions, you get heat. So the system will lose heat. The system loses heat to the surrounding. Our surrounding is going to be water, which means these reactants are inside a flask, and that flask has water as a solvent, but inside the solvent, you're going to have sodium hydroxide in ionic state reacting with HCl in ionic state. When these two guys swap partners, you get sodium chloride and water. If you swap the partners like we did last lab, the other product is going to be heat. So the heat is going to be transferred into the surrounding, which is H2O. So to give you the concept of the idea is this. So the surrounding, okay, so the sodium hydroxide and HCl will lose heat, and that heat Q will gonna go into the surrounding. So that's let me just stop there for now because we're gonna go into the material and you'll know which one is gonna be Q plus, which one will be Q negative. I'm just giving you the introduction right here. So one is giving heat, in this case, the system. The other one is gonna absorb the heat, in this case, the surrounding. That's why when you put a thermometer in the water, to give you a sneak peek of what's coming in the notes, if you put the thermometer in the water right now, during and after the reaction, the thermometer temperature is gonna go up. So change in T will be positive for the water, but the change in T will be negative for the system. So we'll talk about that shortly. So another reaction is where you have acetylene that bonds in oxygen to give you, these two guys will bond to give you CO2, H2O, and the other product, physical product, heat. So the heat can be used to melt glass. So I'm trying to write heat there. The heat can be used to melt glass or in glass blowing process. So the heat can be absorbed by the glass, causing it to be hot, and then the glass will melt, and the glass blower can blow it to different shapes. All right, so I've talked and mentioned about Q. Q, did I? No, I've not mentioned Q. So Q is the quantity of heat. It's the most common form of energy associated with chemical process and is transferred between one system and to another system or to the surroundings. So we're gonna define Q as mass times specific heat capacity times change in temperature. So later in the coming slide, we'll define that formula. But for now, just know that Q is the heat energy. All right, and then using Q, we're going to find the enthalpy change. In this case, because it's a neutralization reaction, the end goal of the experiment in your calculations will be to find the enthalpy change of neutralization. So that's where this is our focus. This is our end goal. This is where we are going. And to find the enthalpy change of heat of neutralization, the enthalpy change of neutralization, otherwise called heat of neutralization, we have to find Q. So we'll find Q of the surrounding, which in turn tell us the Q of the system, which in turn be used to find heat of neutralization. That's the process. So where the reaction is taking in heat, where the system is taking in heat, the system is the reactants, actually. Okay, let's do this. I think that's for the EXO. Where the system is taking in heat, we call that reaction endothermic. Endo means into. So this is into, where the system is taking in heat, the products will have high energy. So those your products, this is your reactants. And I think the difference between the products and the reactants should be the change in heat energy. So obviously the products have high energy than the reactants. The reactants must have gained some heat energy to get high energy for the products. So that's endothermic, and you can see there's a positive change there's a positive change here in the heat of reaction. So this reaction is endothermic. For exothermic, it will be opposite. The reactants will lose energy. So if you were to find the change in enthalpy, the change in heat energy here is going negative because the reactants are up here, products are down here. So such a reaction is said to be exothermic. Okay, this reaction is exothermic. Heat is lost. Okay, so that's how we define exothermic and endothermic. Obviously, you see delta H is less than 0. Heat energy is lost. Okay, so now let's continue. Now we are on calorimetry. Before I discuss calorimetry, let's discuss the setup. The calorimeter is a setup that's used to do or determine heat enthalpy change. And because we are talking about neutralization, we'll be using the calorimeter to determine the heat of neutralization specifically. But you can find heat of fusion, heat of vaporization, heat of so many other heats, latent heat, lattice, all those. So for the calorimeter, you're gonna have a double cup. So we would have used styrofoam. So you're gonna have a baby cup inside a bigger cup. Why? We need insulation. That's the reason. The reason why we have 2 layers of cups is because we need insulation. And the best cup for experiment would have been styrofoam, because styrofoam is a poor conductor of heat. That's why you'd buy coffee in Starbucks. You guys call it Starbucks. I've never bought coffee in Starbucks, but anyway. Styrofoam. You use the styrofoam to make the Starbucks cups because those ones will help you not get burnt by the hot coffee, those who like hot coffee. So it's a poor conductor of heat. But now you use double of them, 2 cups, to make sure that really you're conserving your heat that's within the reactant. So there's no heat loss. That's why you need insulation. Heat can be lost by conduction, that is through solid matter. That's heat loss by conduction. We are preventing heat loss by conduction. We are preventing heat loss by convection, which is through gas medium, like through air. You're preventing heat loss through convection, and you're also preventing heat loss through radiation. That is by waves. So that's why we need the insulation. You're trying to prevent all 3 types of heat loss. So this setup is called a calorimeter. Obviously, once it's done, we cover it. And then up here, we're gonna have a stirrer that goes inside into the inner cup. And then we're also going to have a thermometer. The thermometer will help you read the temperature. So the setup will be as above. You have a thermometer, you have a stirrer, and you have your water in there, which is the surrounding. And then you're gonna have your reactants, which will be the system. The reactants will be the system. For example, HCl and sodium hydroxide, or sodium hydroxide and acetic acid, that will be the system. The solvent will be the surrounding. And of course, everything is capped. So calorimetry is the process of doing this experiment. It's a method for measuring the changes in heat of reaction. So we are talking about measurement of delta H and physical processes, which is heat. It measures the heat absorbed or heat released by the surrounding. If heat is absorbed by the surrounding, then the reaction is gonna be exothermic. If heat is released by the surrounding into the system, the reaction will be endothermic. All right, so that's what I'm saying here. If the system gains energy, then the surrounding has to lose energy. In that case, the reaction will be endothermic. But if the surrounding is gaining energy, if the surrounding is gaining energy, surroundings, if the surrounding is gaining energy, then the system has to lose that energy. In fact, what I should tell you is that energy cannot be created or destroyed. It's just transferred from one system to another. Energy is transferred from one system to another. So, or it's converted from one form of energy to another form of energy. That's first law of thermodynamics. Yeah? So if the system is losing energy, the surrounding must gain it. If sodium hydroxide and HCl are losing energy, the surrounding must gain it. And that's what's going to happen today. Your surrounding is going to be water. So the water will be gaining the heat energy while the system will lose it. Okay? Okay, so let's discuss about first law of thermodynamics. The energy of the universe is constant, which means everything considered, energy is constant, also known as, or also called, also defined as, energy can never be created or destroyed. It's only transferred. Energy can only be transferred from one form to another, from one form to another, or energy can be transferred from system to surrounding, okay? Or energy can be transferred from system to system, but that will be advanced for you. So the one we are focusing on is the second one. Energy is transferred from system to surrounding. So you don't destroy energy. You might break it up, you might divide it, but overall, the sum total is the same. So let's say you are a ski diver or you are on top of Stone Mountain in Georgia. So here you are at rest. So the form of energy you have is potential energy. But the moment you start going downhill, probably you're working out, you're running, that's you running downhill, the energy is converted from potential energy to kinetic energy. It's the same energy. So let's say here your energy stored is 1,000 calories. Then here the energy in motion is still gonna be 1,000 calories. It's just changing the name from potential to kinetic. All right. I really want you to make sure that you know this. For exothermic reactions, the system will lose heat energy. So we put negative. So the surrounding will gain it. If the surrounding gains energy, then delta T is going to be positive. That's our case today because our reaction is exothermic. Okay. What's happening? Okay. Our reaction is exothermic. Do you have a question to that point before I proceed? Unmute your mic if you have the question. I'll give you 5-10 seconds. If you don't unmute, I know that we are on the same page. You understand what I just taught. Okay, silence means everyone is good. Proceeding. So I defined Q as heat energy. It's the heat transfer and it's related to the amount of substance present. That's why we'll need to find the moles of the limiting reactant. And it's also related to the change in temperature and the substance specific heat capacity. So the amount of substance present will be, to calculate Q, we'll use mass, we'll not use moles, but eventually to calculate delta H, we'll need to use moles for the limiting reactant. Okay, what I mean is Q is given by mass, in fact, total mass of the reactants in the system, multiplied by specific heat capacity. In this case, it's going to be that of water, which is 4.184. And then we are multiplying that by changing temperature. Whether the temperature is rising or decreasing, that's what we'll use. It might be positive or negative. So that's the equation that you're seeing here. So if you only considering water, Q, heat energy in the water, will be M delta T times C. Remember, specific heat capacity is 4.184 joules per gram per Celsius. Why this unit? Because specific heat capacity is the amount of energy required to raise 1 gram of a substance. The specific heat capacity is the heat energy required to raise the temperature of 1 gram of a substance by 1 degree. Okay, I repeat, specific heat capacity is the amount of heat energy or the work required to be done by heat energy to raise the temperature of 1 gram of a substance by 1 degree Celsius. That's where this unit is coming from. Heat energy SI unit is joules or kilojoules. If you divide joules by 1,000, you get kilojoules. So the amount of heat energy required to raise the temperature of 1 gram of a substance by 1 degree. That's how we get the units. Okay, then assume we have Q. How do we get delta H, the goal for experiment? So to find the enthalpy change, which is delta H, we'll have to find Q of the system. The Q of the system is going to be equal to negative Q of the water. The water happens to be our surrounding. Okay. So if the surrounding has a positive, Q, which is what we'll have, then our system will be negative. The same value. And that's going to be equal to number of moles of the limiting reactant times the delta. So the relationship that's very important is here. The amount of heat energy of the system is going to be negative that of the water. Okay? So make sure you understand that, because if the surrounding gained energy, then the system must have lost the energy. So the value of the energy of the system is going to have a negative value. And that's what we'll use today, because we're doing an exothermic reaction. So if I have Q of the system, then can I get the enthalpy of neutralization? The answer is yes. All I need to do is to divide both sides by N, the number of moles. This one is not neutralization. That is not the acronym for neutralization. That one is, that's not the symbol for neutralization. It's the symbol for moles. That's the symbol for moles of limiting reagent. So divide both sides by the moles. Heat of neutralization will be Q system divided by the number of moles. That's what we'll need. Now to get the moles, we use this formula. So always, whenever you're given molarity, the concentration, moles will be equal to molarity times the volume, but the volume must be in liters. So today, your limiting reactant will be sodium hydroxide. Its concentration is 1 molar. The volume you need to measure is 50 ml. Okay, so convert the 50 ml to liters. All you need to do is to divide by 1,000 multiplied by 1 liter, because 1,000 ml is equivalent to 1 liter. So you're gonna get this to be 0.05 liters of sodium hydroxide. So now that we have the two units that we need, moles equals to molarity times volume, all we need to do is to calculate, plug in the numbers. So moles equals to M times V. V must be in liters. M molarity times V. V must be in liters. So we come and say our molarity is 1.0. Our volume is 0.05 liters. You know, molarity is moles per liter. So L and L will go. See, you're left with moles in your answer. So it's 0.05 moles. So that's how you find this N right here. Remember, Q of the system will be negative value of Q of the water because water will gain the temperature. Do you have a question? I pause 10 seconds, unmute your microphone and ask. If not, we continue. I give you 10 seconds.
What is the word after H where you say Q system equals in, yes, that word.
That's neutralization, neut.
Okay.
For lack of space, pardon my laziness. It's a Wednesday. But now you realize all chemists like to use shorthand.
Thank you.
All right. And N is number of moles. Good question. Any other question? I really don't want to leave you behind. I want to make sure you understand as we flow. Okay, that means everyone is happy. We move on. For the reaction where you'll have HCl and sodium chloride and sodium hydroxide, sorry, you're gonna need to plot a graph in your report. The one for acetic acid, we're gonna need to use the simulation. That's how I'm doing it for my sections. So we'll plot a graph, and for the acetic acid, we'll try and get a taste of what you should have done in the lab, or kind of pretend it's hands-on. But to explain what you'll be looking for the graph that's needed for your report, I'm gonna use this example that Dr. Philip Vogel put on this PowerPoint. I think it's what you have in your manuals. Whenever you want to do this experiment, you'll first of all, let me see if we can. Let me see if I can pull up the file, because I put the file on Moodle. I think that will help me explain the process. Where is it?
During today's lab, you would have been determining the enthalpy of neutralization of sodium hydroxide with hydrochloric acid and the enthalpy of neutralization of sodium hydroxide with acetic acid. This is going to be done through a process called calorimetry. The first step in doing this is to determine the mass of each of the solutions that will be mixed. We will begin by placing an empty cup on our balance, and the cup weighs about 4.4 grams. We're going to go ahead and tear the balance so that it reads 0, so that we can easily determine the mass of the sodium hydroxide solution. Take the cup off the balance and add sodium hydroxide to the cup. We place the cup back on the balance, and we see that our solution has a mass of 54.164 grams. Next, we need to do the same thing for hydrochloric acid, so we place an empty cup back on the balance. We tear the balance back to 0, remove the cup, add the hydrochloric acid, and then place the hydrochloric acid on the balance. 51.014 grams is the mass of hydrochloric acid in our cup. The next thing we're going to do is determine the temperature of hydrochloric acid solution, and that will represent our very first point on our graph of temperature versus time that we'll be doing. So we take the hydrochloric acid, we place our temperature probe in the hydrochloric acid solution, and our initial temperature will be 24.54 degrees Celsius. Now we're going to get out our calorimeter, which is a large insulated metal container, and we add our HCl to that, sit it inside the container, place the lid on it so that it's fully insulated, and then we're going to add our temperature probe on top. At 20 seconds, we read the temperature of the hydrochloric acid solution, and it turns out to be 24.45 degrees Celsius. We continue this over the course of the next couple of minutes, and we read the temperature at each time, 40 seconds, 60, at 80, 100, and then at 120. At this point, we quickly remove the lid, take the sodium hydroxide solution, and dump it into the hydrochloric acid solution. Put the lid back on the container and get our time at 125 seconds. You can see the temperatures are starting to increase rapidly, and with 30 seconds, 135, 140, 145, and we just continue taking our temperatures until we reach about 300 seconds. We continue on. At 170 seconds, we've reached 30.91, and you see the temperatures are relatively stable at between 30 and 31 degrees. And we just let this finish out until we reach that final temperature and time that we might be measuring. At this point, you would have all of your data collected for trial number 1, and we would repeat this for trial number 2 and trial number 3 for the sodium hydroxide with hydrochloric acid. It works in exactly the same way, but you're going to get a different set of numbers each time. Then we would go back and we would start the experiment over with a fresh solution of sodium hydroxide and a fresh solution of acetic acid. We would perform exactly the same steps that we did in the first place. Measure the mass of the sodium hydroxide solution, measure the mass of the acetic acid solution, take the initial temperature, and then using our calorimeter, measure the temperature for the first 2 minutes and mix the solutions together, and finish out by watching the temperature as it changes, first to a much higher number, and then as it slowly begins to diminish.
Okay. So I think, let's see. So that's, can you hear me, people? I hope so.
Yes.
Okay, that's how these numbers were generated. So you notice that the temperature was stagnant before the mixing began. But once you mixed, the temperature the temperature rises because the reaction, the temperature that's being checked here, by the way, is that of the surrounding, the water. So the system, which is the reactants, these two guys are losing heat energy to the surrounding. So you will expect Q of this, you'll expect Q of the water or Q of the surrounding to be positive. And then you'll expect Q of the system to be negative because it lost, this reaction loses energy, is part of the product. So you see the temperature is going up. So heat was lost by the system into the surrounding. And the mixing point for this one was at about 120. That's where the temperature spiked a little bit. So one would want to draw the mixing line. Let me see where I'm trying to. So you would want to draw a straight line right there. And you have to draw it in your graph. I'll be grading it. So that line marks the time of mixing. Next, you draw the line of best fit using a ruler, not freehand, because the graph is drawn manually on your graph paper. Use freehand to draw, to draw the line of best fit. So where the line of best fit crosses the time of mixing vertical line, that will be the TI. And then do the same thing here for the data points where the reaction was going slow and going over. So where the time of mixing line, vertical line, crosses the line of best fit is called TF. Notice that the line is extended further than the data plots. That's called extrapolation. So you extrapolate to get the best TF. You extrapolate to get the best TI. So don't just look at the data points and tell yourself, I see the lowest point was 24.55, 24.55. Nope. You have to draw the line of best fit and extrapolate. Where it crosses the time of mixing, read on the y-axis. That's going to be your initial temperature, and it happens to be 24.53 or 24.5. And then for the TF, read the y-axis. It's just below 31, so it happens to be 39. It happens to be 30.92, sorry. So again, the highest temperature is not the highest temperature in your data points. It has to be the temperature read from the graph directly. Okay? Now, how do you get change in temperature? The difference between your TF and TI will give you the delta T, which will be needed to calculate Q of the water, because the water is being warmed up by the system after the reaction. So Q is going to be positive, definitely, because there's a spike, there's an increase in temperature. Once you do the math, delta T is going to be positive. Because delta T is positive, because delta T is positive, the heat energy of the water will be positive. Water will be heated up. So which means from here, one can determine that the Q of the system will be negative. And in fact, it's going to be negative the value of Q of the W. Okay. All right, so subtract to get change in temperature. Always do TF minus TI, not the other way around. Always. So in this case, change in T is positive, which makes Q of the water, the surrounding, to be positive. So the reactants will have a negative because they lost heat to the water. Do you have a question to that point? 10 seconds. If there's no question, I proceed. You can unmute your mic and ask your question. If not, I'll proceed. Okay. So we're good. So now let's fix to make Q. Q is equals to M times C times delta T. Some people usually like calling it Q equals to M times change in temperature times C. It doesn't matter, it's a product. So if I like using this because it's easy to remember, one can use the medical test. If you want to go to medical school, you have to take MCAT. So if you want to remember easily the formula for Q, just know MCAT, and you know the A represents the change in temperature. Okay, so that's our formula. So we need M. M in our case is going to be the net mass, the total mass of our reactants in the system. So you sum up 51.002, 54.148. That gives you the mass total of the solution. You need the mass total of the solution because both of them are contributing. So it's going to be mass of the acid plus mass of the base. Okay. So we add them up. That will be the net mass that we'll use in our formula. Q equals to M C delta T. So the Q of the solution will be, in fact, I should say that this is the Q of the not the system, but the surrounding. Of course, the major part of the surrounding is the water. So you multiply the net mass, multiply by the change in temperature, and then multiply by specific heat capacity of water, because water is the surrounding. You get that value. So notice that it's positive. And we expect it to be positive because the water gained energy. The water gained heat energy from the reaction between acetic acid and sodium hydroxide. These two guys will react to give energy, similar to HCl and sodium hydroxide. Both of them will react to give energy. So that will be the system. So when the system reacts, it gives off heat energy as part of the product. That heat energy is transferred to the surrounding, which is the water, which gives the solution. You know the temperature increases on the water, that's why Q is positive. So for the system, the Q will be negative. So if I was asked to find the Q for the system, the reactants, the answer should be negative 28, 11, 11.2652 joules. Why? The system lost the heat energy, and it lost it to the water. The water gained the heat energy. So Q for the water or the solution will be positive, while the Q for the system will be negative because it lost that heat energy to the water. So it's negative. The value is the same. Okay, so use that idea to find heat of reaction. So this is what I just explained right here. So if Q of the system is positive, then Q of solution will be negative. If Q of the system is negative, then Q of the solution will be positive. And this is our case right now. That's our situation for our lab. So remember to find, we derived and said to find heat of reaction is always Q of the system divided by number of moles of the limiting reactant. Turns out that the Q of the system is negative Q of the surrounding, which is water. Okay. Q of the system. So sorry, this is system SYS will be negative Q of the water, negative Q of the surrounding. So we can use, whichever way you interpret these two things. It looks like actually this is what we are using today. The second one, not the first one. Because Q of the system will be negative Q of the water. So I showed you how to find the moles of the limiting reactant. It's always concentration times volume. That gives you the moles. The concentration, obviously you see acetic acid is 1.1. If you try to find the moles of acetic acid, the concentration is 1.1 multiplied by the volume of 0.05 liters. I converted the 50 ml to liters. The answer you'll get here if you punch in into your calculator is 0.55 moles. Do the same thing for sodium hydroxide. It's gonna be 1.0 molar. Molar means moles per liter, multiplied by the volume, which is 0.05 liters. I told you the volume must be in liters. In the formula for calculating moles, the volume must be in liters, not milliliters. So divide the 50 divided by 1,000, you get liters, which will be 0.05 liters. L and L cancels, so the answer is 0.05 moles. Now compare the two guys. The reaction is, if you write the equation of reaction, the reacting ratio is 1 to 1. Acetic acid will have moles of 0.0. Acetic acid is 0.055. Sodium hydroxide is 0.05. So obviously sodium hydroxide is the limiting reactant, and that's what we're gonna use here. Okay, multiply the volume in liters times the molarity of sodium hydroxide, you get 0.05 moles sodium hydroxide. And that's what we're gonna use here in our formula to find heat of reaction. Remember, it's negative. Why is it negative? That's the Q of the system, which happens to be negative Q of the surrounding, which is water. That's what we just said here. Just said here, if this is Q of the water, the surrounding, if it's positive, then Q of the system will be negative. So we are using that negative here, because in our formula for finding enthalpy, enthalpy of neutralization, Newt, we have Q of a system over number of moles. Q of a system is negative Q of water, so we put the negative here. It's the same value, we just change the sign. Divide by the moles of the limiting reagent. Turns out that the answer is should be in kilojoules. So if you do this first part here, the answer will be in joules. But usually to report enthalpy of neutralization or enthalpy of reaction, the answer should be in kilojoules. So in which case we divide by 1,000, because 1,000 joules makes 1 kilojoule. So we use that as a conversion factor here. So you want the joules and joules to cancel. You'll be left with kilojoules per mole. And we have 3 significant figures in our question. So that should be translated to 3 sig figs. Remember the minus. So that minus also tells you that for exothermic reactions, the delta H must be negative. For endothermic, the delta H must be positive. That's how you can tell whether you did it right or wrong. Do you have a question on that slide? I give you 10 seconds to unmute and then ask. All right, next. So this would have been your procedure. I played the video. He explained, Dr. Philip explained the process. So let's go to the report. Download the report on Moodle from Moodle. Once you plot your graph, it should look like this. And this is I only need one graph from the HCl and sodium hydroxide reaction. For acetic acid and sodium hydroxide, we use a simulation. So let's discuss how you'll do it. Remember, everything posted on this first page should be shown in your graph, on your graph paper that you draw manually. Don't use Excel, draw it manually. So these are the data provided for you in red for graphing. The time of mixing will be at 160, not 120. It's 160. Let me see if I can. Oh, what happened? All right, let me just use a pen. So suppose this is your graph. Okay, so this is gonna be your temp, and this is gonna be your time. In seconds, this is how you label your axis. Temp in degrees Celsius. Then the title is enthalpy me find a better pen. Enthalpy. So this is the title. Enthalpy of neutralization. Enthalpy of neutralization of HCl and sodium hydroxide. So that title must be there. So you notice that in the beginning, there is no much change in temperature. So probably your plots will look like that. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So probably like that. And then after you added your acid, or after you mix them together, the temperature spikes. So it's gonna spike. I'm just gonna trace something here. And then it starts leveling off. There'll be a bunch of data points, and then after 20 seconds of waiting will be like that. So your time of mixing in this case will be, the time of mixing that you have to show is somewhere here. Okay, that's your time of mixing that you have to draw with the ruler, and that's gonna be roughly at 160 seconds. Make sure your graph covers as much space as possible in your plotting. And then next you'll need to draw the line of best fit using a ruler. You draw line of best fit using a ruler. Okay, let me try and do it. Where is my pen? Come on, pen, come on. Okay. So tough to do this on space. So line of best fit somehow there. And then another line of best fit. Let me just manually do it because my ruler is not working. Line of best fit that's gonna cross. So you have to extrapolate it. Extrapolate, which means extend the line. And also extrapolate it here. Don't mind about that. We need a straight line. So where they're crossing, TF. Where they're crossing, TI. The difference between TF and TI will give you delta T. Okay, you just have to read the value on the y-axis. Okay, and then TI will be somewhere here. So the difference between the two guys will be delta T, change in temperature. And in this case, it's a spike. So if the reaction was endothermic, it would have been the other way around. All right, so now use that. You're given the mass. I gave you the mass in the table. So to answer, continue answering. So you'll find your TI from the graph. Find your TF from the graph in degrees Celsius. And then here it's asking for the total mass. So you just add up these two guys. You get mass total. And then what else? This is the difference between TF and TI. And then you're given specific heat capacity. Here you'll need the MT multiplied by specific heat capacity multiplied by delta T. Because delta T is positive, again, Q of the water will be positive, which means Q of the system will be negative Q of the water. So pretend that you got 100 joules here. Then Q of the system should be negative 100 joules. But we have to work with kilojoules. So this is the same as negative 0.100 kilojoules. Just for giving an example. So you have to do your own math and find the number. The difference between QW and QS is just the sign. To put the value there, the negative value there, because the reaction is exothermic. I showed you how to find the moles of the limiting reagent. It's molarity times volume in liters. And I think our limiting reagent is sodium hydroxide. So your answer here, if you do your math correctly, will be 0.05 moles. And then I gave you the formula for finding delta H of neutralization. This right here is not moles, that's neutralization. So allow me to just say neut. Okay, that's neutralization. Now remember, QS is negative QW. So I might as well probably just write negative Q of the water. That is QS. Then divide by the number of moles. That will give you the value here. But remember, this value here must be in kilojoules, because you found it in kilojoules here. Q of the system is negative Q of the water, and it's given in kilojoules. You have to use kilojoules. I insist, you have to use kilojoules. One more time, you have to use kilojoules here. Kilojoules must be used, not joules. You find delta H of N. Do you have a question before I talk about the simulation for the next part? Last call, question on the table. All right, so now let's talk about the simulation. This data that we just did goes along with the table, which was used with the graph. So for the next part, I would want you to use simulation. The steps for doing the simulation are on Moodle. So here's your Moodle page, and it tells you where is the step? I thought, okay, so if you click the report, you see it tells you use the second attachment doc for the instruction to answer part 3 of the report involving simulation of neutralization of acetic acid. So let's click this folder. So here it is, calorimetry instruction for acetic acid. That's the simulation. So it gives you the steps to follow. Well, I typed up the steps. I know the steps to follow. So just click the link. It brings you here on an external website by Pearson. So experiment, click run experiment. Then we are not doing liquids or solids, we are doing solutions. So we click the go to arrow and then choose acetic acid. Because we are reacting acetic acid and sodium hydroxide, the volume that you are instructed in the procedure is 50 ml. And then the molarity is 1.1, it's an excess. Show the specific heat capacity of your water. Notice that the temperature now is red. Sodium acetic acid is put into the flask. See, there's a liquid in the flask. The temperature of the liquid is 20 degrees. So we would come in our table here and record the temperature, the initial temperature before we mix it with the sodium hydroxide. The initial temperature reads 20. I put already the mass for the acetic acid and sodium hydroxide. So you can find the total mass, but let's continue with the experiment. So click next, click solutions, then click sodium hydroxide. That's gonna react with acetic acid. Then we also adjust the volume to 50. That's what we have in our procedure. And then we change the concentration to 1.0. I like showing the specific heat capacity to make sure we are looking at the same thing. If you look now, your flask, this is the calorimeter. Your flask in the calorimeter has a liquid. That liquid should be sodium hydroxide, 1 molar, 50 ml of it. And then the initial temperature is 20. So it looks like we have a common initial temperature. So we leave it at 20. We no need to do an average. So next, we click next. I'm ready to do the reaction. We need to pour the acetic acid into the sodium hydroxide. Initial temperature is 20. Once they are mixed, we'll close. The calorimeter closes, is sealed. You see it's a double container, it's gonna be sealed. There's a stirrer that will stir up the reaction. And then this is the display for the temperature during the reaction. There's more instruction here, you can read that for yourself. I want to see the graph. So I'll select show graph. Now, before I run it, I want to tell you that this graph does not show the initial temperature here. You see here, we would have checked the temperatures for 160 seconds for 3 minutes or 2 minutes before we mix. This would be the time of mixing. So the simulation starts the graph at the point of mixing. It does not show the tail. Keep that in mind. So next I click start. So we pour this acetic acid to sodium hydroxide, we close the calorimeter and start reading. The temperature is rising, the graph is going up. So this is an exothermic reaction. The system, acetic acid and sodium hydroxide, are losing heat energy to the surrounding, which is the water. We are checking the temperature of the surrounding, which is the water. The temperature is increasing. So Q of the system, the reactants will be negative. Q of the surrounding will be positive. Okay. All right, so that's the final temperature. The reaction is finished, 26.61. So I would come here. Where is the table? Final temperature, 26.61. Total mass, just add up these two masses of the reactants in the system, you get M total. It's not molarity, it's the mass. So you know how to find change in T. It must be positive. And if it's positive, then Q of the water here will be positive. You have to do the math yourself. Remember, Q is MC, change in T. You already have the M, you have the specific heat capacity, and now you have the delta T. You should find Q. Qs will be negative of Q of water. Remember, this is in joules. Okay, this will be in joules. So you'll have to divide by 1,000. You have to divide by 1,000 to give you kilojoules. It's the same value, just put a negative and divide by 1,000 to make it kilojoules, like we did in the previous table. I already showed you how to find the moles of sodium hydroxide. Just multiply by volume in liters. It's the same number of moles, 0.05. I would expect it should be 0.05 moles. Pardon my pen. Let's clean up and make sure it's clear enough. So moles. All right, and then now you find heat of neutralization. This should be negative Q of the water like we did. And it must be in kilojoules. I cannot insist that enough. It must be in kilojoules like it was found here. Negative Q of W, which is generally Q of the system, divided by the number of moles should give you delta H of neutralization. All right, so that ends my explanation, and you need to show your work calculations, watch your significant figures, and that's your graph. You need to draw it manually. Make sure your graph covers much of this space. All right, there are two more questions at the end you need to answer. Do you have a question before I end the lecture?